Hey, good evening, everybody. This is Michael Porter, Muddy Boots Code. Hey, I'm a data science enthusiast. Love to play around with all things Python, Graph, and also just all sorts of web development stuff. I'm joined, as always, thankfully, by Nathan Smith, an actual data scientist currently working with Love Every, and he helps us out every day, gets us going, helps us where we stumble and fall, and sifts all of the wheat from the chaff as we go along. Today, we're going to be talking about in our data science group number 10, the bootstrap. We're working in selecting samples and working with distributions and stuff like that of data and ensuring that we get the best data from the things that we work. Last meeting, we talked about the bootstrap a couple of times, and I was kind of like, well, what is the bootstrap? We haven't got there yet. And then now, we've worked our way to what the bootstrap method is. Um, and just after a quick perusal of the chapter and kind of going over some stuff and looking at notes, it's basically a way to take a number of samples from your population and and just get different ones every time. It's you kind of generate not false but like mock data. Is that kind of accurate?
Yeah, that first sentence there where it talks about estimating the sampling distribution of a statistic. So what we're trying to do is we've got our whole population, which is unmeasurable in many cases. So I'm going to take a sample and then I look at, say, the mean out of that sample and figure that that must be somewhat close to the mean of the overall population. And the sampling distribution says, well, what if I took a whole bunch of different samples and measured the mean of each one of those? How would those means be distributed? Right? Well, maybe it's not really feasible for me to gather a whole bunch of different samples out of the population. Maybe I've just got one sample, but I still want to estimate how variable would that mean be um, if I repeated that sampling process over and over again. Um, and this bootstrapping gives us a way to do that without having to get 100 different samples. I can just resample out of the one sample that I drew, and I can still get an estimate of um, what the overall population would look like if I resampled it a whole bunch of times.
Okay, so yeah, but just like it says there, you're drawing additional samples with replacement, and that's the big thing. You're replacing what you took out instead of excluding those from again, and then from the sample itself, and then you recalculate the statistic or model for each resample.
So, it's coming from that observed data set. So, maybe I've got a certain um, group of people that are supposedly representative of the whole population. I'm not going to find more groups of people. I'm just going to use that one group that I started with, but I'm going to slice and dice it in different ways by resampling with replacement in such a way that it gives me a sense of what that statistic would look like if I could draw, sample 500 more groups of people or something.
Got you. Yeah, down here, it's conceptually you can imagine the bootstrap as replicating the original sample thousands or millions of times, so that you have a hypothetical population that embodies all the knowledge from your original sample. It's just larger, just bigger. So from this hypothetical population, we can estimate the sampling distribution. And again, like you said, you have your original sample, and then you replicate it however many number of times, and we go on. It says here that it's not necessary to actually replicate the sample a huge number of times. We can just replace each observation after each draw as we sample with replacement. And in this way, effectively create an infinite population in which the probability of an element being drawn remains unchanged from draw to draw. So it's pretty simple there. The algorithm for Bootstrap is for size n is as follows. So we draw a sample value, we record it, and then replace it. And then we repeat that n number of times. Now, my question there at the n number of times is, so like, let's say you have a city and it's 10 million people, and you've done a sample. You're able to get statistical data on 10,000 people or whatever. If you wanted to then bootstrap that sample to the theoretical size of the city, you would just do it n number of times until it was almost 10 million or close to, right?
Well, I don't have the formulas to estimate the confidence intervals at the tip of my tongue, but you remember earlier in last week's chapter, we saw um, a picture, a histogram of the sampling distribution, and the two things were how big was the sample and how many times you resampled the data, and the more times we resampled and the bigger the size of the sample, then the narrower that bell-shaped curve got, right? It got more pointy. So that's the same idea here, that the more times you run the bootstrap samples, and the bigger the sample size each time that you resample, the more precise your estimate of that particular statistic can be.
Okay, so doesn't necessarily have to like approximate like the total population of what you're trying to do. Okay. So then we record the mean of the in resampled values. We repeat steps 1 through 3 R times, whatever R is. It says use the R results to calculate the standard deviation, produce a histogram or box plot, and then find a confidence interval. And as I kind of in my mind, I was like, okay, well, you do this like until you had an approximate size. But this is saying that the number of iterations of the bootstrap is just kind of set somewhat arbitrarily. The most iterations you do, the more accurate the estimate of the standard error or the confidence interval.
So really, the driving factor determining how many times is enough is how much uncertainty you're willing to tolerate around that confidence interval. So if you need to know the value with a really high degree of precision, then obviously you need to keep repeating it until you get enough information to give you that level of precision.
Okay. So again, from this, the results from this procedure is the bootstrap set or sample statistic or the estimated model parameters, which you can then you can examine to see how variable they are. It goes into R, but since we ain't jacking around with R, we'll go ahead and skip over to Python. It does say that in R, there is a specific package that deals with bootstrapping, but in Python, there's not. And so in order for to do the bootstrap in Python, you actually just kind of have to do some manual, pick your R that you're going to use and the stuff that you're going to do, and just run a regular old for loop across it and check it out. I have, let's see here, code up for that, where ran it here, and it's just not exciting. Not a whole lot to show there in this. We had the resample.
What if we talked about what was the right R value there? They set R as 1,000. If we change that to 2,000, does it change the bias or the standard error?
Let's restart our kernel here. See if that rocks along. See if we can run this. Oh, hold on. We got to go back up here and
import our library.
Import our library. All right, let's try that. Oh, still not the right one. All right, let's just run it down.
There we go. We're probably getting close now.
The bootstrap. That's running 2,000. So our original size, our bias 83, standard error is 2233. Let's run that at 1.
So you see they both came down a little bit with that additional 1,000 runs.
Right.
So if you ran it and realized, oh man, I really need to be, the standard error needs to be smaller than 227, well, you just run it some more times and you get a little bit more information and you can potentially.
Gotcha. Yeah, it's one of the things that it talks about here soon is that essentially that the bootstrap method has been known about for a long time, but initially it was too computationally expensive to be used and to be widely accepted because it was just too hard. Now, we can just run it in Jupyter Notebook or whatever, how many times, or run it on our local machine and see what we get for it. You said, bootstraps can be used with multivariate data, all this different kind of stuff with classification and regression trees, running multiple trees on bootstrap samples and then averaging their predictions generally performs better than using a single tree. Process is called bagging, which is short for bootstrap aggregating. And then we go through there. So the repeated sampling of the bootstrap is conceptually simple, except this is, in 1969, they were talking about it and they were doing stuff, but because it was so computationally expensive, people didn't make use of it like we do now. So this is particularly popular among researchers who use statistics, but not statisticians, but who aren't statisticians. Seems to make sense. And again, it talks about here, the sampling distribution of the mean has, been well established for a long time. And then the rest of it, we kind of work off through that. So it says down here that initially, the bootstrap method was met with considerable skepticism. It had the aura to many of spinning gold from straw. And this skepticism stemmed from a misunderstanding of the bootstrap's purpose. So that's kind of like, I guess I would see with that where they're like, oh, well, you're just making up populations, you're just making up numbers, and that doesn't match with what we're actually trying to do, right? So the bootstrap does not compensate for a small sample size. It does not create new data, nor does it fill in holes in existing data sets. It just informs us about how lots of additional samples would behave drawn from the population like our original sample. So then we get resampling versus the bootstrap. And then sometimes the term resampling is used synonymously with the term bootstrapping as just outlined. I can't talk sometimes. It happens like that. More often, the term resampling also includes permutation procedures where multiple samples are combined and the sampling may be done without replacement. In any case, the term bootstrap always implies sampling with replacement from an observed data set, not necessarily the permutations and stuff that are included in the resampling. So again, our key idea is the bootstrap sampling with replacement from a data set, and then bootstrap can be applied in similar fashion in a wide variety of circumstances. It allows us to estimate sampling distributions for statistics where no mathematical approximation has been developed. And when applied to predictive models, multiple bootstrap predictions outperform the use of a single model. And then it gives us some further reading, an introduction to Bootstrap by Bradley Efron and Robert. I'm going to butcher this, and I'm sorry if you're out there watching this, which is highly unlikely, but Robert Tibshirani was the first book length treatment of the Bootstrap and is still widely read. A retrospective of the Bootstrap in the May 2003 issue of Statistical Science, and then an introduction to statistical learning by Gareth James, Danielle Lewitton, and Trevor Hastie, and Robert Tibshirani, again, who, please don't call me out for crushing your name there. It was a little messy. One of the things it does do, and I don't know if you want to go over this, it gives us a link to permutation testing, or permutation tests. You think you could, like, off the top of your head, give us like a little breakdown of what permutation tests are?
Well, I didn't really brush up on this, but when we think of
Oh, come on. What kind of data scientist are you? You don't know this stuff off the top of your head?
Right. Well, when we think of permutations in set theory, there's combinations and then there's permutations. In combinations, the order doesn't matter. And in permutations, the order does matter. So, if I've got like the letters here, A, B, and C, in permutations, CAB is not the same thing as ABC because they're in a different order. And so whenever we're permuting something, then we are changing the order. So the step 2 there, where it talks about shuffling, that's where the permutation comes into play. So I guess we could just talk through this, that we've got A/B testing. We hear about that a lot in web design, where
Absolutely.
we've got 2 groups that are exposed to a different treatment, and we see how their results differ, right? And so we're going to put the 2 groups together, and if the treatment that we do doesn't have any effect, then we should be able to shuffle them up, the people who got treatment A and the people who got treatment B, if we would just shuffle them up and then redraw the people, so there's no rhyme or reason into which group that you ended up in. We're going to draw you out. If the difference between the treatment and control groups after you shuffled is the same as the difference before you shuffled, then the difference before you shuffled really wasn't significant, is what we're saying. Right? If you might look at a number and think, oh wow, the people who got A really did a lot better than B when you just look at it. But then if you shuffle the numbers, if you do a permutation of the people and then you look at them again and you still see a big difference, it probably means that you've just got some outliers in the group, that some people just really responded a lot more than everybody else. And that's what's driving the differences between the groups. It's not necessarily that all the A's and all the B's really have a big difference between each other.
Got you. So in this one, like I said, it just gives that breakdown, like you said, of, where you're going to have your groups, and then you're going to combine the results from the different groups into a single data set. You shuffle that combined data and then randomly draw a resample of the size of the group. And then for the remaining data, you randomly draw without replacement a sample of the same size of group B and C and D and so on. And then you collected one set of resamples that mirror the size of the original samples, and whatever statistics or estimate was calculated from the original samples, calculate it now for the resamples and record this is one pure permutation iteration. And then you repeat the previous steps r times to yield a permutation distribution of the test statistics. And then we just go back and we look at the difference between groups and compare it to the set of permuted differences. And then if this observed difference lies well within the set of permuted differences, then we have not proven anything. The observed difference is within the range of what chance might produce. And if the difference lies outside most of the permutation distribution, then we conclude that the chance is not responsible. And so then that means it's statistically significant.
Mm-hmm.
So there we go. So we have an example here of web stickiness. I have not read through this, and so this would be probably terrible to just stumble through. So we won't expose people to that. If they want to look at that, they can do that.
Yeah, but the connection with bootstrapping is in both cases we're drawing subsamples out of our sample data. But the important difference is that with the bootstrapping, every time you draw somebody out and look at it, you put it back in the pot. So you've got just the same exact chance of drawing them again as you did the first time. Whereas with the permutation test, we are not necessarily putting them back in the pot. You're just drawing out a bunch of people, put these guys over here, put these guys over here, and examine them at that point.
Now, how often do you say you use that?
Well, you know, most of the questions that I get called on to answer are not really about what is you know, a descriptive statistic. What is the mean of this population or something like that? The kinds of questions that I deal with at work are much more often classification questions. Is this person going to cancel their subscription, or are they not going to cancel their subscription? Or you know, they could be regression questions in terms of what's the lifetime value of this customer or something like that. So I'm trying to pick a number, but it's not necessarily a descriptive scenario where I would use bootstrapping in this form very often. Where the bootstrapping does come into play in my work most often is in the context of a random forest model, where it's happening behind the scenes to help me develop a more accurate classification.
Gotcha. Okay, so those are all good examples right there. Yeah, I can see where you're probably like your populations and stuff are probably pretty well like or more well defined, I guess, maybe than maybe something that we're using for this.
Yeah, I mean, you know, if I were working on a political campaign and trying to estimate who's going to vote or you know, the underlying demographic situation in a particular region, this kind of modeling would probably be much more relevant, or looking at population health kind of things in the medical field. This kind of sampling might be very relevant.
Okay. Yeah, that makes sense. So as it goes on, we've got a few more code examples here. Again, if this is your thing, feel free to jump in there and do these on your own. We're not going to jack with this because it's not obviously not the next thing in the notebook. It's probably somewhere else, but works out pretty good.
Yeah.
So end of our chapter. We had the further readings that we've already gone over there, and the next data science topic that we're going to look at will be confidence intervals. So we will look at that. And meeting number 11, hopefully we'll be joined by the ever mysterious Jeremy McGraw. We'll see if he pops up for us there. But unless, sir, you have anything else, I think that's pretty good for tonight.
I agree. Have a good evening.
All right. Thanks, everyone.